Okay. So, as I said, this is a for 1810. So, this for record also. So, this will be clipped 1810 lecture. So, we multiply two arrays A, B and the result is in C. Okay. So, we want to do using Numba. So, there will be Python code and we just parallelize part of it, but Numba you can specify Numba CUDA. Numba has a CUDA module. With that you can specify threads and shared memory and blocks, all that. So, in fact, like what you do for C, you can do it with Numba in Python. And I would like to check the speed. I did not check the speed up, but that is something which I would want students to tinker around. At least some of you should do it. Okay, so, this part is so let us go through it slowly. So, this is already got inside. So, thread per block. So, this is another well, we have two arrays A and B. So, thread per block is 16. So, A is what? What is the size of A? Is 32 by 48, right? TB star 2 and TB star 3, and B is 48 into 16. When I multiply, what will be the size of C? C will be 32 by 16. Okay. So, this is C is 32 by 16. It has more rows and columns. This is schematic. Is taken from book on CUDA actually. I think it's this author. So, I did not reference it. This from that book. So, 32 by 16 and this is part of the main program, like host code. This is part of the host code. So, we create these arrays A, B. Okay. Fill in by 1. So, testing is easy, right? If I put random number, then I do not know whether my code is correct or not. So, I fill up with 1. So, you might see is behind that thing num pi ones and is filled up with ones, and this is also filled with ones. Okay. A, B is filled. Now, I transfer it to device from CUDA to from CUDA dot device. What will it do? It will take this array A, which is in the host. So, it is going to send it to GPU. Okay. And what is the name of this GPU array? It is A global mem. Okay. So, that is name of the, maybe I should use a different color, A global mem. Similarly, I transfer B, but C I create an array. So, that is called device array function. So, this part of CUDA I did not write it in top. So, import from Numba import CUDA. So, this CUDA is a module and is this 32 by 16 TB2 star 1, right, and this. Now, this standard what we do in CUDA. So, thread per block. So, we right now I am creating blocks and threads. Okay. So, blocks and sorry, not grid, blocks and grid. So, there is a block. How many threads each block has? TPB by TBV. So, 16 by 16. It is in a square grid. So, it has 256 threads. You can organize threads in any way you like. So, it is organized in a square array. Now, I also want to make grid. So, grid is grid X is A shape 0 divided by blocks per block 1. So, I divide this is 16. So, A shape 0 is 32, right. So, 32 by 16 will be 2, this is 2. Along Y is B shape 1 divided by block 0. B shape 1 is a y direction, okay, 0 1. So, 16, this will be 1. So, my grid is basically 2 by 1. Each of them 2 blocks. So, this is the grid will tell you number of blocks. So, 2 blocks, each of them are 16 by 16 thread blocks. So, this is a line here. So, this is a block 0, block 1, clear. And so, we create for this block for C. I am going to multiply A and B. Okay. So, now I will just call this function mat mul. matrix multiplication. So, how many threads and blocks I am using? So, blocks per grid, which is 2 by 1. This is a we just said 2 by 1 is a tuple. It is not a list, but it is a tuple 2 comma 1, which is going to come here. Sorry, it will come here 2 comma 1, and threads per block. Threads per block I already declared is 16 by 16. So, we are basically creating this stuff C, okay, space for C. So, every entry of C has a thread, that is what we want. Okay, we will compute for every entry of C, okay, and the arguments are A, B, C, global memory. So, this arrays are already in global, and I am going to use that as an argument. And after I get the result, then I will do copy to host. So, I take this C and I copy to host. So, the syntax is a bit different, but idea, the flow is exactly the same as what you do in CUDA, and I print for my testing. So, now let us look at how does matmul look like. So, matmul is a very small function. This is a simple function. So, A, B, C, there are 3 arrays in the global memory. So, then I get row comma colon equal to CUDA grid 2. Okay. So, this is a grid is a function of CUDA. It tells you the global location, global row and global column. Okay. It is a function it knows this grid function knows your full allocation. So, it is going to tell you what is a row will be in that direction and column will be in that direction. Okay. So, in fact, given the grid and the block, this for the given grid and block. Okay. I think I did cover how to get x and y given grid and block. Okay. So, if you have two blocks and each block has threads, so I can go to any position by some formula. In fact, just a straightforward formula, block size multiplied by the block ID, number of blocks before plus thread ID, okay, and we can do the same thing along x direction. So, anywhere I want I can get the position, global position. So, x in row and column are the global positions. Okay. If row is less than C shape 0 means x dimension, and column is less than y dimension, right, for C, I loop temp is 0, then I do k in range A shape 1 and temp is updated. So, what do I do? A I k B k j is equal to C I j. I is row and j is column. Okay, is it clear? This is straightforward. And after I get all this, I just write it on C row comma column temp. So, C is in global memory, it will get updated with temp, which is the answer, and in the host code you saw that this will be C will be written to the, this is in GPU memory right now, but it will go back to main memory. Clear? But this code is not very good. Why is this code not very good?
We are taking everything from
Global memory, and that is expensive. So, when I get all this stuff, it is getting from global memory. So, I should try to use shared memory. Okay. Shared memory access is fast, global memory access is slow. So, let us do one example where I will try to do a simpler problem than this. I will not do it right now in the next slide, but I will do it after 2 slides. So, simple problem where I will use shared memory. So, how do I declare in CUDA? Not CUDA, Numba dot CUDA. Okay, that's so shared array equal to CUDA shared array shape and type. Okay, so you can give the shape means x y dimension or x y z dimension, and type is the float or integer or whatever. And this one thing is CUDA sync reads. So, when I am we need to sync threads, sorry, not sync threads. So, you see that if you are operating on, well, this is a shared memory where many threads are acting together, no? You saw, well, we will see in the example, but please remember that shared memory many threads will act on the data of the shared memory. A shared location where everybody comes and does their operation, like they come for tea or they do gym, and you have to make sure that everybody finishes the task before you take the next step. So, let us look at what I am going to do. So, I am going to do it for simple. So, that multiplication is slightly complicated. So, I am going to do a multiplication where I will use two arrays which are of same size, 16 by 16, 16 by 16. Well, actually the in this book the diagrams are written like this. So, this is A and this is B, result is here. It is nice presentation. Huh? So, A, B are not side by side. So, we can get the column here and row here. Okay, so, that is a nice presentation. So, B is above, C is in the side of A and below B. So, let us look at this simple example, and if you understand it, then you can understand the even bigger problem. It is a faster method. So, that other function, the function I am rewriting. Okay. So, fast matrix multiplication, but under the condition that A, B, C are of the same size. So, I create two shared arrays SA and SB. So, CUDA shared array shape is TPV, TBV 16 by 16 I said no, and this is also 16 by 16, and type is float 32. Okay. Now, I get XY location from the CUDA grid. So, XY is basically row and column. Okay. Then I get the thread positions TX, TY. So, please remember that how many threads are running right now. So, it comes from the host code, right. So, this will have only one block. It's there is no two blocks. The earlier code had two blocks, but there is only one block which has 16 by 16. So, you have to make sure that there is only one block is running it, and it is 16 by 16. So, the tuples will be 1 comma 1, 16 by 16. So, this will be grid and this will block. Okay. Clear? So, each guy is running it. So, let us so I am going to make this diagram a bit bigger here. This is C and this is B. Okay. So, for a given thread X and Y are here. So, this is X, this is Y. So, by the way, for this is single block. So, X equal to Tx, right, because single block, if there are more blocks, then X can be different. Thread X is a local, basically it is a grid ID, a thread ID in the block, but X is a global position of the element in the global array. Okay. So, if it is only one block, then thread ID and X are same for X and Y as well. So, Y equal to Tx. Ty, sorry, Ty. Okay. Well, I mean this is a, if you are going outside, do not do it. So, temp is 0, then I do this AC Tx comma Ty is A Tx Ty and SB Tx Ty is B Tx Ty. It is a trivial statement, but what is it doing? So, given Tx Ty, so for A and B I have created respective SA and SB. They are shared arrays, but it just copied. Well, how many guys are acting on during the copy? 16 by 16, all of them are acting. So, whole SA will be filled and SB also will be filled. The copying also will take time because it is coming from the global, but you do it once. Okay. So, my shared memory is loaded now. By the way, even in a block, the number of threads cannot exceed 1024. So, I cannot use, for example, 64 by 64 in a block. Okay, that is exceeding 1024. No. So, 32 by 32 is possible, but not 64 by 64. I copied it, then do thread sync. So, these two copies should have been completed by all the threads. So, this is what is going to do thread string. Then I can multiply and get so SA. So, I am doing this AIK BKJ here. Is it clear? Now, what is the advantage by doing this function over the previous function? Because the data is in the shared array, so this is faster. I do not need to get it from all the time from the main memory. Okay. So, in fact, it is just simple idea which improves the code performance. And CUDA thread string, because this is, by the way, this is done by all the threads. Huh? This is something which it took me some time to get used to it. So, there is no loop. So, every txt, every thread with id t, well, with id tx comma ty is doing it. So, after this operation, the full C will be filled by the correct result, right, because this multiplication done at temp. So, I forgot to put temp is 0. Temp is 0 is here. So, temp is 0 is here. Every thread has their own temp. That is a local, their local stuff, and that will be updated. No, sorry, I did made a mistake. No, temp is local only. Okay, so local only for txty. Yeah, for C there is a local. For every txty there is a temp, and that will be updated here for xy. Okay. Yeah.
Like
Private type. Okay. Yes. So this works.
So,
Yeah.
so but still on hardware level, the memory is separate, right, for CPU and GPU.
Yes, but I am not looking at CPU memory at all in this. Global memory is a GPU memory. The GPU has 24 GB or 48 GB. Okay, A100 has 40 GB. Global memory. That's when I say global, that means is the GPU memory, not the CPU memory. Okay, and keep it in GPU memory, whatever you are working with. Any question? Okay. Now, let us be adventurous and do the bigger problem. Okay. Now, this is done using a stencil. I did not put the word, so this is called tiles. So, I am going to use several tiles. Okay. So, let us get the idea first. So, now this is at 40. So, this is 32 by 48. You see that 32 by 48, and this is 48 by 16. You definitely know that we have take a row here and a column here and multiply, right? That is what we do. So, take this stuff and incline. So, you can see this yellow strip is being multiplied. So, in the previous example, we just took one block and multiplied, right, and that did the work when all of them are same size. But now, to get a value at Cij, I need to work with the bigger line, bigger row or bigger column that cannot fit in a shared memory, right. So, that is my, or number of threads. I can't make a big block for shared memory. Whether every block has their own shared memory, which is limited. Also, the block size, the number of threads in a block cannot exceed 1024. So, we create 3 blocks for A and 3 blocks for B. This is called 3 tiles. Okay, they are basically called, these are tile 1, T0, T1, T2. This is T0, T1, T2. So, I am going to multiply T0 with T0 with a very similar idea what I did before, T1 with T1, well, T1 of A with T1 of B and T2 of C with T2 of C, and add. So, each operation will have local total and then add it up, and you have to do it for every x, y. Well, it is parallel, so all the threads will manage it. So, we need to create how many threads? Not 16 by 16, 32 by 16. So, this is, so 2 blocks and each block is 16 by 16. Okay, so, you just sort of think a little bit more after my you add the code, and you should be okay. So, this is the code. So, this part is exactly same as before, this is also same, but now x y is the global row and global column. So, this x y is sitting here for a given thread, for a given thread. Now, we create T x and T y. So, now we have more blocks and more threads. So, you have to be T. So, T is T y local, and look at this function. This is the most important. Well, this is the 3 lines are the important lines. So, SA I want to fill. Okay. So, given x and y is filling this SA T x comma T y as a x comma T y plus I T B V. I goes from what to what? A shape 1 divided by T P B. So, A shape 1 is 48, right here you see 48 by 16 is 3. So, I takes value 0, 1, 2. So, this will give you the position here or here or here. So, for given x y, by the way, please remember x and T x are related, it is not arbitrary. For the first block T 0, x is same as T x, for second one will be 16 plus T x, third will be 32 plus T x, and same with y. So, here every guy is doing it. So, let us imagine I is 0. Okay, then what do you expect for when I is 0? It will do what I did in the previous example. All these guys will act together and fill this T 0 and T 0. True or not true? So, you can just see that when I is 0, x comma T x, which is same as T x comma T. Right now, x will be for T 0 is T x comma T y. Sorry, x will be T x. So, for I equal to 0, it is exactly same operation what I did in the last slide. Clear to everyone? This is T x comma y, which is T x comma T y. So, SAN is will be filled up, and then I do this sync and temp, CUDA sync threads. So, all these guys will do together. Now, for every temp, I will get the Cij for T 0 tile. Now, I want to go to T1 tile. So, I will go in the loop and increment I by 1. Okay, then what is going to happen when I goes to 1? So, x is shifted now. Okay, when I go to I, so I am working, well, sorry, not x is not Tx and Ty is shifted, and so I should not say that. So, my position in A will be shifted. X is fixed here for given thread. For given thread, x is fixed. Now, Ty will be this Ty and this Ty are different. Is shifted by 16, correct, because this is I am just adding this 16. So, now I am filling T1. So, when I do this operation, I go I equal to 1, then I filling T1 tile, and I again do the same operation. So, every x y is getting, for every Cx this guy is getting the next additions Ai k bjk bkj. I am doing this Aik bkj, but this k is shifted each time, and when I go to I equal to 2, then I get the third tile, this third tile. Okay, and once I done with the 3 tiles, then my temp has a correct Cij for given ij. So, I put it here, Cxy is temp, and then in the host code this is copied, Cxy is copied to the main memory. Okay, it's a clever idea actually. It took me some time to get it, but it's a very clever idea. So, you are doing it in parallel, and this is fast. One reason is all these guys are working together to get Cxy, but it's in one shot. Okay. In principle, you should take 1 unit of time instead of n squared n cube time. right. When I do a loop, how many do I j from I equal to 1 to m, j 1 to n, k 1 to n, and that is NQ operation. Of course, copying and all that takes time. This multiplication will take time, but this is just one clean boom, one shot. So, this is a collective thinking, okay, and it's a clever ways to solve a problem. Isn't it clever? I mean, this is a. So, this is how we multiply matrices in CUDA or in GPU rather. So, this is I am doing in Numba, but CUDA also this code is there in CUDA in some several references you will find it. Okay, so I thought I will explain this clearly, and it's a very good way to use collectively.